So welcome to our lecture series on quantum computing and general introduction. I say for mathematicians, but we can say for non-physicists. We started at a very interesting level the last time. I would like to start the second lecture by a short recap of what we discussed last time. And as you recall, last time we presented some very basic concepts of quantum computing, the notion of superposition, entanglement. We saw mostly measurement. We analyzed what is a measurement. We realized that the simplest realization of a qubit, of a quantum bit, is a photon. And we discussed certain properties of photons that actually transfer to the case of qubit, because the photon is the simplest realization of a qubit. So today we are going to continue this discussion by focusing on multi-qubit states. And we're going to see how these concepts are, what form they take in the new setting. So let me get started. Here is the outline of the talk. I'm going to remind you what is a quantum computation, this concept of storing and processing information. And we realize that understanding quantum computation is somehow related to understanding the notion of processing information and transferring information. I'm going to discuss the concepts of quantum superposition and entanglement for multi-qubit states. I'm going to show an example of measurement of a multi-qubit. We are going to discuss again the issue of entangled states. This concept is very closely related to quantum computation and to the property that has been proved in many cases that quantum computation provides a very big speed up in connection with the classical computation. And the issue of entanglement is very intimate connected to that. We're going to discuss what are three views of quantum computation, starting from the circuit models of quantum computation. I'm only going to tease you with the concept of quantum parallelism and one slide of source algorithm. This is a very deep concept, and we're going to devote a full lecture in the second semester. But at the moment, I would like you to get some idea about what is the so-called source algorithm, what it is about. And as you recall from the last lecture, this is what was the reason that the quantum computation as a field took off. The fact that Peter Shor, a mathematician, managed to create this algorithm that shows polynomial speed up in the discrete log, and we're going to say more details about this starting today and in the second semester. So let me start with, again, this picture that I showed you the last time. What we saw the last time is I presented to you these two, as I call it, the giants of quantum computing, Richard Feynman and Yuri Manin. They realized that certain quantum mechanical effects cannot be efficiently simulated on a classical computer. And then the question arises, is the following: what will it mean for computation if it were grounded in quantum physics, the actual physics of the universe? So, and then the second question that arose was, can these quantum effects be used to speed up computations? What else can they do? So what I mentioned the last time also, I just want to mention this again, is that the first quantum algorithms that were created provided results with the deterministic results. Even though results that were proven in classical computers with high probability, they were able to create algorithms that were giving the result with certainty. And that was counterintuitive because everybody thought that quantum mechanics is of probabilistic nature. So this is something that we're going to discuss more in depth in the future, and it is something that you should be aware. So as I mentioned the last time, what made the field to cope was the realization, starting from Richard Feynman in 1981, who realized that nature isn't classical, and if you want to make simulation of nature, simulations of quantum mechanics, you'd better make it quantum mechanical. He thought that classical computations with classical computers is like a brute force. So you needed something that will create more efficient computations, and in his mind was machineries that rely on quantum mechanics. So this is the background, and this is something that it has to be clear throughout these lectures, that just because a computer makes use of quantum effects does not make it a quantum computer. Even this computer this simple laptop makes use of quantum effects. Nobody can claim that this is a quantum computer. So what a quantum computer does is it actually changes our notion of information. And this is what I mentioned here, and this is what I mentioned the last time. So what a quantum computer does, it actually changes the notion of information and on how you process information. So in that sense, you go from logic to quantum logics, from algorithms to quantum algorithms. So by storing and processing informations stored in quantum states, a quantum computer can solve certain problems dramatically faster than classical computers. And we have examples of polynomial speedups and exponential speedups. In this category, there are some even mathematical problems, like approximating topological invariance, and certain computations in algebraic number theory. In the case of polynomial speedup, there are examples with regard to unstructured search, collision finding, graph properties, etc. So let's see what, so we know what a quantum computer is not, as we said. Just because a laptop uses quantum effects doesn't make it a quantum computer. Can we give a definition of what is a quantum computer? Well, a loose definition is the following. It is a controllable machine that receives inputs using quantum mechanical effects to run quantum algorithms and provides outputs. If we wanted to put this loose definition in a mathematical framework, we will say that instead of using 0 and 1, as in the classical computers, quantum allows superpositions. This is the linear combination of these two states, alpha, 0 state, plus beta, 1 state. And if we want to write down what are these state vectors, this notation corresponds to this two-dimensional vector. This notation corresponds to this two-dimensional vector. So we can represent any two-dimensional vector as a linear combination of these two. So in some sense, the space of qubit states is isomorphic to a two-dimensional complex space. So as mathematicians, we know that when you see this symbol consists of equivalent classes. So I have to specify what is the notion of equivalence that we are using. And another issue that we discussed the last time is the issue of measurement. So when you have a superposition of that form, we get 0 with probability a squared, alpha squared, and 1 with probability beta squared. So what I wanted to say is what is the notion of equivalent classes that we use in connection with this space. So we say that two linear combinations, two superpositions, A0 plus B1 and A prime 0 plus B prime 1 are considered the same value if one is the multiple of another for some modulo 1 complex number. So you can think of this number as something of the form e to the I field, something of that sort. So it has to be modulo 1 complex number. So this is, let's say, the most mathematical definition that we have regarding quantum states, quantum computer, of the notion of quantum computer. And I would like to continue discussing this concept of superposition. I have written here, as you can see, two quantum superposition at the top, and they are both 0 and 1. The one has a plus sign, and the other has minus I. So we start with these two superpositions. So let me just make some comments that we discussed the last time. The superposition 1 divided by square root of 2, 0 quantum state plus 1 quantum state, does not mean that the particle is a half time at 0 and half time at 1. Or it does not mean that the particle is at least two positions with the same with some probability. It does not even mean that the particle is in states 0 or 1, we just don't know which. So there are all these. This concept of superposition can be very tricky and confusing. This superposition is a definite state. You know, if you consider the example that we did the last time of polarization, if you have a photon that crosses, has an angle of 45 degrees, and it goes and consider a Polaroid of degree 45 degrees, then you're going to see that the photon will pass through the Polaroid. So what I'm trying to say is that this superposition is a definite state that when measured in a certain basis, deterministic results are obtained. So it is not as vague as one would imagine. But when measured in other bases, the results are probabilistic. The description above, this description ignores the significance of relative phase. And this is something that we're going to see some examples later on. So it turns out that really discussing what is superposition philosophically, it can be very tricky, but mathematically it is straightforward. And that is the beauty of mathematics, of being able to do things through the lenses of mathematics, because then you can give more precise definitions. So we saw the last time how we measure a single qubit, and we saw that measuring this superposition in the computational basis 0 and 1 returns 0 with probability a squared, returns 1 with probability b squared, and projects to the basic states corresponding to the measurement results. And what is the story here? Is that as soon as a qubit measurement takes place, the particle is no longer in superposition. So at that point, and for that reason, only one classical bit of information can be extracted from one qubit. As soon as you do the measurement, things change, and you can only get one classical bit of information because the state is no longer in superposition. As I mentioned here, a qubit can be measured with respect to any orthogonal basis for its two-dimensional state space. Another interesting point here that makes measurement interesting is the so-called no-cloning theorem. You cannot really reliably copy a quantum states, and that affects the way that measurement takes place. Hackman. So this is a slide that I also presented last time. The question that we tried to address was what happens if you combine multiple qubits together. And we're going to see more about this today. So if we start with the vector space X, with the basis alpha 1, alpha 2, alpha n, and the vector space Y with the basis beta 1, beta 2, beta m. So X is an n-dimensional vector space because there are n elements in the basis, and Y is an m-dimensional space because you have m elements in the space, then as you recall, classical state spaces combine via Cartesian product. So Cartesian product, the basis of the Cartesian product of these two vector spaces is described here, and one can easily see that the dimension of the new space is simply the sum of these two spaces, the dimension of space X and the dimension of the space Y. So this is not how quantum states combine. As we saw the last time, quantum states combine via tensor products. So here, this space has bases that consist of the tensor product of the corresponding element of the two bases. And as a result, the dimensionality of this space is much larger. Instead of addition, here we have multiplication. So now that we have seen enough of the about this material, let's go to more in-depth discussion about the multi-qubit states. So the only thing that I need you to have in mind is that this new space now is much larger than you had before. Okay, this is an important point that you have to consider. So let's consider here now the quantum state of an n-qubit system. This is a vector space in the 2 times n-dimensional space. In the classical space, we have 2 times n parameters. In the quantum states, since each particle can have 2 choices because they are written with respect to a 2-dimensional space. If you are a spin, it will be up and down. If you consider polarization, you can consider different directions of a Polaroid. So even the quantum state of n-qubit system is a vector in this 2 to the power n dimensional space. So if B is the state space of a single qubit spanned by 0, 1, then a 2-qubit system has this basis now. You see, the basis consists of the 0 tensor product 0, 0 tensor product 1, 1 tensor product 0, and 1 tensor product 1. So often we write this representation in a simpler form, and this form is the following: 0, 0, 0, 1, 1, 0, 1, 1. So we are going to follow this notation in the next slides and discussion. But please have in mind that when you see this symbol, it simply means 0 tensor 1, for instance. So if we wanted to write down the standard computational basis of the 2 to the power n dimensional complex vector space, which is given here, of an n-qubit system, this has this form. So you can make the computational basis as large as you want. So, and this is something that I discussed also the last time, because I wanted to point out the different world between classical simulations and quantum simulations. If you consider a general n-qubit state, this can be written as a linear combination of this form. Here with AI, we denote the various amplitudes. And in this case, we have to have a certain normalization that the sum of AI squared is equal to 1. This is our qubit state. And as I mentioned the last time, since the space of the number of parameters in the classical case is so much smaller than the dimension of the quantum state of the new space, then you can see that most states cannot be written as a tensor product of individual qubit states. That means that all states can be written as a linear combination of such states. So let's see what, and that brings us to the concept of entanglement. states that cannot be written as the tensor product of individual qubit states are called entangled states. In a quantum computer, entanglement is used as a sort of computation multiplier. That's why very often you see the statement that entanglement is the concept, the property that allows us for speed up in the quantum computation. And as I say here, entanglement also can be a weak point because the smallest kind of interference from the outside world can break the fragile correlation between two or more qubits. So let's see some. I just want you to see with a simple calculation here. We have a 2-qubit state. I just want you to see once written down. This is a 2-dimensional vector. I don't even use the qubit notation, the physics notation. I use a math notation. Like say, let's consider this psi. Now we know that every qubit is a 2-dimensional, can be expressed as a 2-dimensional vector. So if we consider 2 qubits, psi and phi, if we wanted to find what is the tensor product, or very often it is known as Kronecker product of this vector, this is simple calculation, and I just wanted you to see this once. See, the qubit, this qubit, tensor product P, means that you take this vector, tensor product, this vector, and this essentially what you do is this simple computation. But this shows that you start with two vectors that are 2-dimensional, and you end up with a vector that it is a 4-dimensional vector. So, and this is the general principle in this case. Given 2 single qubit states psi and phi, each of the dimension 2, the corresponding 2 qubit state psi tensor phi is a 4-dimensional vector. This vector can be expressed in this form and represents a quantum state on 2 qubits if we require that this relation holds true, that the sum of the square powers of these quantities are equal to 1. So most of the things that we have told today is somehow a review. In Greece, we say that η επανάληψη είναι η μητέρα της παιδείας, which says that repetition is the mother of knowledge. So I feel that this small recap will allow us to go for a little bit deeper on some of the concepts. So I would like now, we saw how simple it was to measure a single qubit. Let's see an example of measuring a multi-qubit state. And here we want to measure the second qubit of this expression, this three, how can we say, what is the actual, so here you see, yeah, so what we're going to see here is that we are going to measure, to do this measurement by measuring bits cube individually, and then we are going to reduce this measurement into the measurement of the single qubit. So if we wanted to measure the second qubit of this expression in the computational basis, then what we do is we project the state on the subspace where the second qubit in state 1 and returns 1 with probability. Okay, if you are here in this case where the second qubit is in the state 1, then the subspace where the second qubit is in space 1, it returns 1 with probability A3 squared plus A7 squared, because in these two cases, this subspace returns 1 with this probability. The new state is the result of the projection. So the new state that we obtain is what we had here, because these are the two states that returns the second qubit in state 1. So we have to include these two states. A3, 0, 1, 1 plus A7, 1, 1, 1. But now we have to normalize it. So we have to divide by 1 divided by the square root of A3 squared plus A7 squared. So if we wanted to do the equivalent thing, measuring the second qubit in the case where the second qubit is in state 0, in this case, the subspace where the second qubit is in state 0 returns 0 with probability what? It is the remaining 1 minus A3 minus 7 will be A0 squared plus A1 squared plus A5 squared. So the new state in this case, it will be given as the sum, as the linear combination of these qubits with the corresponding amplitudes and normalized in such a way so that we have the appropriate unit length that we need. So as you see, the spirit of the approach is very similar to what we had in the case of simple measurement, single qubit. And here is an example. As I mentioned earlier, entangled states cannot be written as tensor products of independent units. So here is a very famous example of such a state. It is called the EPR pair. E stands for Einstein, Brodowski, Rosen. So this pair is given as a superposition of 0, 0, and 1, 1. So let's argue, as mathematicians, let's argue by contradiction. Let's assume that we can express this as the linear combination of individual qubits. You see, I take this multi-qubit state, and I say, let's assume that I can find A0, B0, A1, B1, such that this relation holds true. If you come here and you use the simple calculation that we did earlier, you are going to see that by performing this tensor product, this becomes A0, A1, 0, 0, plus A0, B1, 0, 1. You recall that this notation means 0 tensor product 0, 0 tensor product 1, plus B0, A1, 1 tensor product 0, 1, 0, and B0, B1, 1, 1. So this is what we have. So as you can see here, the only way that this could be equal to 0 and this equal to 0, because this is when we will have the right argument, is if A0 B1 is equal to 0, which means either A0 is equal to 0 or B1 is equal to 0, or B0 A1 equal to 0, which means that either B0 is equal to 0 or A1 is equal to 0, which means that in this case, even these two guys will be equal to 0, which is a contradiction. So this is a nice example of a nice example that we can consider. So what else? Comments. Let me make some comments here. If you do measurement of the first qubit, then typically you get either 0 or 1. See, the next measurement changes the state to either 0, 0 or 1, 1. Measurement of second qubit gives the same result as the first. So somehow this combination of the two things, the fact that the measurement changes to either 0, 0 or 1, 1, and then you measure again. If you measure again of second qubit, this gives the same results. It is something that confused Einstein a lot, because he immediately thought that this meant that you may have two particles in the very different parts of the universe that can exchange communication. And that means with a speed faster than the speed of light. But in reality, the situation is not as that, and the paradox has been resolved. And we will discuss a little bit more about this in the future. So let's see, this concept of it turns out that these states, the so-called entangled states, are going to be really important for quantum computation. And here I want to present three views of quantum computation, starting with a quantum circuit model. This view of quantum computation is closer to the heart of computer scientists. And of course, you're going to tell me, why do you call it circuit model? Because as we are going to see in the next slide, the way that, the notation that we are using in order to define this model resembles the electric circuit. So how does the story goes here when you have a quantum circuit model? In this model, you start in a non-quantum state, and then you proceed by applying a sequence of 1 or 2 qubit quantum logic gates. And I'm going to show you an example in the next slide about this. So when you, as mathematicians, we should be very, despite the notation that it is used in these lectures, when you think of qubit, think of a two-dimensional vector. When you think of gate, think of a matrix. So let's try to make things in our mind as simple as possible. I'm going to show you examples of gates in a second. So what we're going to see that the way that this form of quantum computation works is that you start in a non-quantum state, and you apply a sequence of 1 or 2 qubit quantum logic gates. I'm going to show you examples later. And you measure in order to find the final answer. So these steps seem very well defined and very concrete. Then there is the next view of quantum computation that we discussed in detail last time in the RIT, actually, the so-called adiabatic quantum computation. So in this particular case, we have to define a Hamiltonian, a final Hamiltonian. I denote here HF. If you want to think of what is a Hamiltonian is a function that has a form of an energy. If you think of Hamiltonian, think of energy. If you ever have to come up with a Hamiltonian, think of the form of the energy of the system and try to choose the appropriate function. So define the final Hamiltonian whose ground state is in the solution to the computational problem under consideration. So you define the final Hamiltonian whose ground state is the solution of the computational problem under consideration. And you start in the ground state of an easily implemented Hamiltonian, and then you evolve very slowly. As you remember, this is very important in the context of adiabatic quantum computation. And then you measure to obtain the final answer. We will see all these concepts in the last RIT lecture. I noted a couple of slides for this process where we can spend lectures in the second semester on this topic, actually. The third type of view of computation is the so-called measurement-based quantum computation. So here in this setting, we start in a highly entangled state that serves as the quantum resource, make a series of single qubit measurements that depend on the result of previous measurements, and then interpreted the results of the measurements to obtain the final answer. So here are three kinds of views of computation. I'm going to spend a little bit of time in the circuit model of quantum computation. And as I mentioned earlier, you are going to see the reason that this model of quantum computation has this name is because we can express it in a way that looks like an electric circuit. So a quantum computation in this context consists of an n-qubit register. You remember, I call this register psi. You remember what is a register? You can think of it as a component of the computer that carries information. And then what we do, we apply quantum state transformations of the register. That means a sequence of primitive 1 or 2 qubit operations. We call them gates, UI. You are going to see it in the next concept. And that collectively perform the transformation of the register. We proceed with a measurement of sum of all qubits of the register. And of course, in this particular setting, we need to ensure that we have classical control throughout the process so that to program which quantum steps to carry out and also to offer the appropriate interpretation of the results of the quantum measurement. So let me show you this example. Here, you can see usually we go from the left to the right. Our register is, we denote it by psi, and you can see what is happening. We have a gate that applies in the center to qubits. Here is I, U1, I. Then we apply two gates, U2 and U3. And this form indicates the location. And subsequent, we apply the transformation U4. So this is the physics notation, or this is the mathematical notation that only explain how you can, by thinking of these quantities as operators. So, and here are some examples of gates. Some single quantum gates are presented here. The first two do not need any explanation. The first is the identity. It maps 0 to 0, 1 to 1. The second is negation. It maps 0 to 1 and 1 to 0. Okay, I should have written there 1, 0. The most interesting and sexy one written here is probably the variable phase shift, which is denoted by T of alpha. And this gate, when it is applied to the quantum state 0, it creates a phase shift indicated by this quantity and this quantity here. So what is the interesting part here is that since alpha is a real number, this notation defines an infinite number of quantum gates, really, by this single one. Another, of course, you can consider a combination of this. And a combination of all this can be seen here. And this is the change of basis, H. This here may remind you the example of the Polaroid that goes through a 45 degree polarization. And so this gate maps 0 into this superposition and 1 into this superposition. And I would like this to become clear that there are infinite many single qubit gates. We can create as many as we want, because every time that you consider change of phase, you can have as many gates as you want. So let's go to the next topic. The next topic is multi-qubit quantum gates. So what I want to emphasize here, it turns out that if you have this gate, that it is called the control node, together with all single qubit gates, it's a complete gate set. You can consider and you can develop any algorithm that you need and that you want. So the combination of this control node gate together with all single qubit gates, it's a complete gate set, and you can do any quantum algorithm with that. So the control node here, as you can see, it is very, very simple. It just flips the second bit if only if the first bit is 1. So you see what is happening here, that here is the control node. It only flips the second bit if the first bit is 1. So here it is 0, so it remains the same. You come here, this is 1, it flips to 1, 1. if you are here, this is 1, it flips to 1, 0. So this is a very important gate. For this, the reason that I mentioned that together with all single cubic gates is universal for quantum computation. And here are some observations that are very typical for this sort of things. All quantum gates are linear, actually unitary. Quantum computations are reversible. Quantum gates do not dissipate energy. This is something that we are going to discuss extensively in the second semester, because we are going to see the combination between the relation between the concept of energy and quantum computation. So I'm not going to spend time. Is there a question?
No, I was just.
I'm not going to spend a lot of time on that because we are going to discuss it again in the second semester when we discuss algorithms, and we're going to discuss the various complexity classes. This topic is of great interest for computer scientists, and these are some very important quantum classes, and I would like to discuss a little bit this diagram that shows the relation between the various complexity classes, but we need to have more discussion about complexity theory, so we are not going to spend a lot of time on this. One few words about, again, this is a topic that we are going to spend lectures in the second semester, and I hope that this lecture will not be given by me. We are going to recruit other experts in the field as well. So the quantum error correction is a very important concept. As I told you, when Peter Shor created the theorem, created the source algorithm that actually shows how to factor any integer in prime numbers. That immediately people realized the connection of this result with standard encryption systems, because implementation of such an algorithm could break a lot of security systems. What made the people less panicky was the fact that they realized that quantum computers are very fragile, and they thought, oh, it will take a lot of time for something like this, like the source algorithm, to be implemented. What made the community worry is when the field of error correction start making tremendous progress. As I mentioned here, quantum error correction initially thought impossible, and the reason is that we have no cloning principle, and a known quantum state cannot be copied reliably without destroying the originally. But then it turns out that a group of mathematicians, and Robert Calderer is in Duke in electrical engineering, but he had done a lot of mathematical work. Steen, Shor, and Calderer saw a way to finesse what had seemed insurmountable barriers to quantum error correction. So there are a lot of advances in this field that was made by mathematicians, and that's why I think we should dedicate several lectures on the topic of quantum error correction. So at this point, the quantum error correction is one of the most developed areas. It is beautiful. People very often call it magical. It uses properties of quantum measurement and entanglement to its advantage. So it is something that we will spend a lot of lectures in the second semester. Of course, the next topic that is of interest in this context is that everybody knows that error correction cannot be done perfectly. So one has to, and then the field of fault tolerance came into front, and fault tolerance ensures error suppression, correction. So what is the fear here is that by trying to do error correction, you may introduce even more problems and errors. So, and fault tolerance ensures that error correction do not introduce more problems than they solve. And these problems usually arise due to imprecise implementation of mechanics may cause error, and even accurate implementation may magically magnify errors. So there is a realistic worry here, and this field of fault tolerance has developed a lot in the recent years. And one of the main important topics that has of great interest to mathematicians is the establishment of threshold theorems. Theorems that say that there exists an error rate threshold below which indefinitely long quantum computations can be carried out, or related concept. One of the major open questions in the field is how to establish a threshold theorem for the adiabatic quantum computing. And this is one of the major open problems that is of great interest for mathematicians, actually.
Can I ask something?
Yes, please.
So could you just say a few words about this adiabatic theorem, because I don't have an image for how you evolve from a Hamiltonian to another one. In my mind, Hamiltonian evolves the quantum state.
So you consider linear combination. I can show you. You are oscillating between two Hamiltonians. You create something, how do you call it? A linear combination, like a convex combination of Hamiltonians. So you can consider, well, this is what I mean by a convex combination. You consider a convex combination of two Hamiltonians. In the current lecture, I was calling it H naught and HF. So the adiabatic theorem of quantum mechanics says that if a quantum system is prepared in the ground states of a time-independent Hamiltonian H initial, and the Hamiltonian is changed to H final in some time, then the system will remain in ground state of all the instantaneous Hamiltonians passed through, provided that the changes is made sufficiently slowly. And this is the nature of the word adiabatic. So we have, I thought that I had an example here, but I don't have it right now. But we can talk about this even at some other lecture, actually. But basically, you oscillate between an initial Hamiltonian and a final Hamiltonian, and that means basically that you monitor the evolution of the energy of the Hamiltonian in this sort of consideration. So I want to bring this to, we have only 5 minutes, but I just want to show you these 2 slides in order to introduce the concepts that I'm going to discuss in the next semester. One is the concept of quantum parallelism. So what I'm saying here is that by linearity, a superposition of inputs yields a superposition of results. And what is the story? The story is that a quantum circuit can be applied to all 2 to the power n possible input values at the same time. To obtain the superposition of all values from 0 to 2n minus 1, we need to create a mapping of that form. For any sufficiently uniformly, this is what we are going to discuss, why this is true. For any sufficiently uniformly computable classical function, f, there is a quantum circuit UF that computes the output in a superposition in time comparable to the computation of a single value of a classical function. So this is the thing that we're going to devote a lot of time trying to prove next time. When you apply this operator on this qubit, what you obtain is that the value of the first component remains the same, and on the second component, you obtain the function f of x. So in this setting, if you apply this operator in this superposition, what you obtain is a superposition of this form, where now here you have this function f of x. So this becomes very interesting if you consider it. Consider an example, and an example that is typically given in this setting is the quantum Fourier transform. If we consider fa to be the classical Fourier transform of a vector A, there is an efficient quantum algorithm Q such that when you apply the efficient quantum algorithm to this superposition, here are the amplitudes, and here is the quantum states, then what you obtain is a linear combination, the superposition of the mapping of F acting on this vector A with a reference to these qubits that depend on J. So if UF is a quantum algorithm that computes a periodic function F, then when you apply this to this linear combination, you obtain precisely this function. So, all right, here is a thing that needs a lot of discussion. Measuring the second part of this, of the register, yields a random value x and collapse the state to this. Where these amplitudes here are non-zero, if and only if this function fi is equal to x. And in this setting, you can write that applying the quantum Fourier transform on this qubit, it gives you precisely the outcome that you want. So why I mentioned this? Because this idea, and we're going to discuss it again, this idea of quantum parallelism, especially in the way that it is applied with the Fourier transform, is very instrumental in the breakthrough that was done by Peter Shaw. And I'm not going to devote a lot of time, but I just want to say that it is a major result in another theory that says that to factor an integer m, it suffices to find the period of a function f of x equal a to the power x modulo m for some random a. And this is where the source algorithm, the concept of quantum parallelism is very important, because in order to find the period of this function, you have to apply quantum parallelism. You compute f for all 2 to the power n values simultaneously using quantum parallelism. And we're going to see each step, because each step is very involved. And then you apply a quantum Fourier transform to get only multiples of the inverse of the period. And then you measure. And of course, if there is an error, you have to repeat again. But the point is that this algorithm succeeds with very high probability. So in any case, this is all I have to say for today. Are there any questions?